Right, okay then, so next up is part 7 of our Key Stage 4 look at waves. So what does this entail? What are we looking at? We're looking at dispersion and total internal reflection. So in our last lesson, we were talking about reflection and refraction. If you didn't watch that, or you don't really know what those two are, I would recommend you go and at least do a little bit of research about it, or go and watch the other video, which would be good. As dispersion, it really is a natural progression on from refraction, and total internal reflection is, as the name suggests, obviously a natural carry on from reflection as well. I'm going to assume that you have that, you know what I'm talking about, so we're going to carry on. So dispersion, as I said, this is a natural progression on from refraction. Now what we're going to do in this example is basically talk about visible light or white light. As we were talking about in previous lessons, we were talking about the electromagnetic spectrum. And we know that the visible light, the light that we can see, is just a really small, around middle-ish part of that electromagnetic spectrum. Now, inside that visible light, there are various frequencies of light waves. So it's a big mixed mash. It's actually got a spectrum within itself. So as we were talking about when we were talking about refraction in the last lesson, as the white light comes in from this gas low density medium that it goes into a prism. So this prism is a higher density, can be made of glass, perspex, but because of the rules of refraction, as we were talking about, as it goes into a denser medium, it starts to slow down. These different frequencies of waves are affected in different ways. Now, generally speaking, the higher the frequency of wave, the more the wave is refracted. So, as you can see, as we have with our electromagnetic spectrum, we had infrared just below just underneath the visible part of our spectrum, and we had then going up in, especially the same with sound, we had ultraviolet light on the above side of the visual light, or the visible light that we can see. So as we know that ultraviolet has a higher frequency, wave frequency, than our infrared. So as we would suggest, our red, or the red part of the spectrum of visible light, is actually refracted less because it has a lower frequency than our blues, indigos and violet spectrum of the visible light, because it has a higher frequency. So don't forget that, it's very important. The higher the frequency of the wave, the more it is refracted through a higher density medium, or through our prism that we have here. So as I said, this is why our blues, our indigos and our violets are refracted a lot more than our reds and oranges, because the blues, indigos and violets have a higher frequency of wave. So this splitting of white light, splitting it into its 7 composite colours, is what is called dispersion. Now this is exactly how we see rainbows. What's actually happening there is exactly what we can see here, is sunlight is going into a prism. In this case, sunlight is actually, in the case of rainbows, sunlight is actually going into tiny water droplets up in the sky, and as it goes through those water droplets, it's dispersed out, it's refracted out into its separate colours, and that's exactly why and how we can see a rainbow. It's just basically the dispersion, the refraction of sunlight that gets split into these different frequencies of the visible light spectrum that we can see. So key point, don't forget, the higher the frequency, the greater the refraction, so therefore the indigos and the violets are refracted a lot more as it goes through a prism, so therefore they must be a higher frequency than our reds and our oranges at the top. So that's dispersion of white light. That is generally what dispersion is. So we're going to move on, and we're going to have a look at what's called total internal reflection. So this again is it's a semicircular prism. It's going to be maybe perspex or glass. And what we have here is what we were talking about in terms of putting a light beam straight through. So what we have here, remember our incident angle, what we call an incident angle. At this point, our incident angle is 0. So that is why there is no refraction, there's no reflection, because the angle is 0, it is moving straight through our perspex object. Now, as we were talking about previously in refraction, we know that the angle of incidence, as it moves through our object, as it moves from the object into back into the air again, there should obviously be some refraction here as it moves into another object, but as the beam comes through and goes into our other object, this creates our angle of refraction here. Now we know this again, which is exactly the way that we were talking about. It goes from a denser medium into a less dense medium, so therefore it's pulling away from our line of normality, here. So as we know, as we were discussing before, if the line moves away, if the beam moves away from the line of normality, that means that the light beam is actually speeding up, which we would expect because it's going from a high density object into a low density object. Now as you can see, our angle is beginning to move round. Now when we get to the point that actually, this is called our critical angle. Now, critical angle is where our light beam stops actually exiting the other side of our object that we're putting the light beam through, and actually travels at 90 degrees to the plane of that surface. So we have our line of normality, which is actually the point of refraction, which is right here, okay? So it's actually the critical angle is the point that our light beam comes in and actually travels along exactly the same line as our semicircular prism that we have here, our semicircular perspex. And this is the critical angle. So at the critical angle, there is no longer light being refracted back out into the air, and there is no light actually being reflected back. It's actually travelling along the surface or along the edge of that line. Now, what happens here after the critical point is where we actually get in to what is called total internal reflection. So the critical angle is actually the changeover from where refraction is occurring and from where what we call total internal reflection occurs. So what's actually happening here is that the angle of the beam coming in has reached the point that it no longer refracts out here, no longer refracts here, it no longer refracts here. But what it's actually doing is reflecting back from the inside surface of the edge of the material. So what we've actually got here, as it's gone into our semicircle, is actually reflecting back off the inside edge of this prism. So if we imagine, you know, if we take a 3D picture, this is the semicircle that we've got coming in here. So as our beam comes into this part, what it's doing is actually reflecting off the inside surface of this part of our semicircular perspex. So this is what's called total internal reflection. Now the reason why this is, as it said, is because it can no longer actually refract away. It's got to that certain point that it actually just bounces straight back again. So, you know, what's the point of this? What's the use of this? Well, there's actually lots of modern day uses for this total internal reflection. Back in the old days, you still get them periscopes. You know, you've seen them in the old submarine films. You know, if you ever played armies as a little kid, you could have made periscopes look out of trenches and things. And this is all to do with the reflection from one mirror inside to a glass into a side. You can take the, it could be a mirror, or in this case we're using a glass prism. And it's just the angle where it's actually reflecting back from that inside surface, back down onto that inside surface again and into your eye. And this is all internal reflection. Reflectors as well that are on your bike uses, again, prisms, using internal reflection of the actual glass prisms. But most importantly, or maybe not most importantly, but the most widespread modern use of total internal reflection is from optical fibres. Now, you know, optical broadband you can have, you can get your digital TV through it now as well. And what this actually is this tube here is insulated with a really non-reflective surface on the outside, but then on the inside has a really highly internally reflective material. So in this case it could be glass. So what actually happens is your light ray comes in and it uses this total internal reflection to be able to carry straight through this tube. So these optical tubes, these optical fibres, you know, it could just be a snazzy light in your living room, or, you know, as I said, you use this for sending digital data for broadband and digital TV. So yeah, this is a modern use of total internal reflection. So that was our look. So we looked at exactly what dispersion was. We're looking at total internal reflection, and also looking at abbreviated TIR, that is total internal reflection, what it's actually used for, how it can be used in the modern day, and how it's been used for a number of years, really. So yeah, that's our look at our two things there. That's the end of today's lesson. Our next lesson, we're going to be looking at something slightly different called diffraction. Okay, yeah, my name's Ian McDowell, I'm a student at Brighton University. Thank you.